In this technical support video, I'm going to be discussing how we can model wavelength changing phenomena such as fluorescence in FRED. I'll be using the current development version, which is 10.40, but the feature that I'm going to be using that allows this to be done very easily is also going to be available in the release version that we're expecting any day now. So I'm going to go ahead and start here with an empty FRED document. I'm going to set up a very simple fluorescence model where I'm going to be using a volume fluorescing material. So let's go ahead and start by defining a source here. I'm going to use a detailed source. We'll call it blue source. Set its positions to be, let's say, 301 by 301 on the ray grid. Half a millimeter is fine. I'm going to go ahead and make it elliptical. It's going to be traveling in the positive z direction. I'm going to offset this slightly from the origin by -1 in z and hit apply. Okay. Now this particular source, I haven't assigned it wavelengths yet, so I'm going to go ahead and use FRED's spectrum feature. So I'm going to go ahead and create a new spectrum. We'll call this blue spectrum. It's going to be a sampled spectrum. I'm going to go ahead and import these tabulated values from a text file that I happen to have. So it's called royal blue. And here are the values, and I can go ahead and plot this spectrum. Okay, so here's the royal blue spectral distribution. Notice that it goes out to about 0.5 or so. I'm going to open up my source again, and I'm going to assign it wavelengths. By default, we use as specified by list, so I can go through here and assign some wavelength and weights. I've created a spectrum, so I'm going to randomly generate wavelengths according to that spectral distribution. You can see it goes from about 0.4 to 0.5. Hit OK. So here's my source. This source is going to be passing through a simple plane parallel plate. I'm going to say it's 2 millimeters in diameter. That's fine. I'm going to give it a length of about 1/4 of a millimeter. Reference it to the back surface. Coding, I'm going to leave this uncoded, so I select bare surface. That's going to be uncoded, allow all in the ray trace control set. I can hit OK. Actually, let's go ahead and assign its glass material. It's to standard glass, which is a BK7 equivalent. Okay, so here's my geometry. Let's go ahead and throw an analysis surface in here. Make it -1 to 1 with 31 divisions. Hit OK. And I actually am going to be passing rays through the plane parallel plate, and I'm going to be looking at the color image actually exiting the plane parallel plate. So let's go ahead and assign the analysis surface to the front end of our plane parallel plate here. Okay. Now how are we going to model the wavelength changing phenomena? There's two places that we have access to change the wavelength during a ray trace. That's going to be the scripted surface scatter model. So I could have created a surface scatter model, go create new scatterer. We'll do scripted BSDF. Let me expand this out so you can see it. And you can see that one of the parameters we have access to here is G_W, which is the wavelength of the ray. I'm going to go ahead and use actually a volume scatter model. And I've assigned standard glass. So if I open up the standard glass material, you can see that one of the tabs we have access to is called volume scatter. Okay. One of the types we can choose is user-defined volume scatter. Now, similar to the surface scatter, you can see that one of the variable values we have access to is G_WAV, which is the wavelength of the ray that's undergoing the scattering during the ray trace. So we'll come back to this in a second, because if I'm going to be generating random wavelengths for the fluorescence model, I need to know the distribution, the emission spectrum over which I'm going to be generating those wavelengths. So I'm going to go back to the spectrum here, and I'm going to create a new spectrum. Let's call this emission spectrum. It's also going to be a sampled tabulated wavelength value pairs. In this case now I've grabbed a image from the literature of a particular emission spectrum, and I can go ahead and use FRED's digitizer to pick the wavelength and value pairs out and create this sampled emission spectrum. So if you didn't catch that, it was right-click in the spreadsheet area and do digitize curve. Select an image. I have a BMP of YAG-CE here, this emission spectrum. Span this out. I'm going to go ahead here in the digitizer. I select my minimum point, so that's going to be at 0.3 microns. Y origin value of 0. I select my maximum. It's going to be 0.7. My Y maximum, let's go ahead and say it's 1 up here. Now I can go ahead and select some data, so I'm just going to start picking some points off of this emission curve. Hit export to data, and now my emission spectrum has been tabulated. So it goes from about 0.5 on upwards. Let's go ahead and hit OK, and we can go ahead and plot our emission spectrum. And here's the curve we just digitized. Okay, so now that I have an emission spectrum, if I hover over its icon, you see that it has in brackets 1, and then it says sampled spectrum. During the ray trace, I don't want to make a lot of unnecessary function calls. So a typical script might include something that says find full name or find spectrum, and then I give it the name of the spectrum. That'll return to me the node number. During the ray trace, for efficiency, I'd rather just explicitly give it a node number so that I'm not making an additional function call for speed. So let's go ahead and make a note that our emission spectrum is spectrum node number 1. Go back into our standard glass here. Click on the volume scatter. We're going to turn volume scatter on. I have to specify a scatter coefficient here. 1 will do. It's going to use that for all wavelengths if there's only one defined. Let's give it 0.1 mean free path in system units. So that'll ensure that probably scattering 1 time as we pass through this volume here. Under type, let's go ahead and select user defined volume scatter. Expand this dialog so we can see what we're working with here. I'm going to go in, and I don't need most of this stuff here. I'm going to go ahead and just delete it all. What we do need to do in this script is, first of all, change the wavelength, and then also give the ray a new set of direction cosine vectors here. G underscore U out, V out, and W out. So let's start by changing the wavelength. So I'm going to say, first of all, the wavelength variable here is called G underscore wave. So I'm going to go ahead and say, if G underscore wave is less than 0.54, then we're going to do something. Why do I say that? Because the ray coming in to this system, remember, it's a blue LED, so the wavelengths are going to be less than 0.54 microns if they have not scattered yet. Once they have scattered, their wavelength is probably going to be changed in the fluorescence, so we don't want to go through this whole process again. So we're just going to scatter the one time for wavelengths less than 0.54 microns. If that's the case, then give the new ray wavelength equal to spectrum get random wavelength. Remember, this emission spectrum had node number 1. Okay? And that's all we need to do. So Fred's going to use that spectrum we just created. It creates a probability distribution for that and picks a random wavelength on that spectrum. Now we need to give the ray some new direction cosines. So let's go ahead and say dim A as double, B as double, C as double. Okay. A is going to be 2 times G R1 minus 1. What is G underscore R1? If we go up to the header here, we can see that we're given 4 uniform random numbers between 0 and 1, so we can use those however we want. Okay, similarly, B direction cosine is going to be 2 G underscore R2 minus 1. And lastly, C equals 2 times G R3 minus 1. Okay, now I'm going to go back through and set the direction cosine vectors here. GU is equal to A, GV is equal to B, GW is equal to C. And this essentially is isotropic scattering here. Go ahead and hit compile. We can see the script compiled with no errors. We should be fine. Let's go ahead and hit OK. And I'm going to go ahead and do a trace and render now. Keep in mind that we're starting with a blue source. I'm going to do a trace and render so we can see that the rays are scattering, and then I'm going to stop it partway through for speed. So you can see the rays are scattering inside this material, coming back out towards the source, going through. Let me stop it. For speed, I'm just going to go ahead and trace without rendering. This will be a lot faster. Now I'm expecting that rays that are passing through this plane parallel plate undergo wavelength conversion and are changed to a different color, giving us what we might expect something like white light for this emission spectrum that we've chosen here. So the rays have finished tracing. I'm going to go up and do an analysis and a color image. Hit OK. And here's the color image for rays exiting our plane parallel plate. If I move around in here, you can see that we're on the very warm white side, shown in the lower right hand pane where the crosshairs are moving around towards white. So we've changed our source rays from a blue distribution using the YAG-CE emission spectrum and a volume scatter model to convert to a white light. Now the whole model is based on the fact that we now have access as of version 10.31 to this spectrum get random wavelength command. This makes our lives much simpler for modeling these sorts of wavelength changing phenomenons.